Hello, this is our workshop number one. So I'm pretty much going to guide you through, well, I guess the first workshop. I'm also going to introduce you on everything that we're going to do. So that's pretty cool. So we're going to have 6 workshops in total, and it's all outlined in this document called Electrical Workshops, which is in the theory. We might change it to projects, but it'll be the same link. And then workshops, electrical workshops. So let me just go through this. So we're gonna have 6 workshops in total. The first one, I'm going to just introduce you to electronics. All right, so we're gonna get Altium set up. I'm gonna introduce the electric vehicles, and we're gonna show you the schematic that, or the PCB that you're going to making in the next 4 weeks. So after this, we're gonna do schematic design, then PCB design, then PCB exporting, and then we're going to have a battery workshop where we make a battery and do some welding. It'll be cool. And then we'll have an integration workshop. So there's a lot of exciting things. So anyways, this is our workshop number one, our introduction. So I'm going to be following this guide. So just as a preface, this is a recording for you to listen like when you have time, right? But Demir will be in person to do these workshops on your specified times, like Tuesday. All right, so the first thing is getting Altium license set up. So if you look here, I made notes on all the workshops. Right now I only have 1 and 2, but I will continue to add it as the term goes by. And pretty much, if you go on this link right here, we have access to Altium, right? And if you scroll all the way down, there's a little form right here that's asking you to start the verification process. So you can put in your school email and your institution. Voila, and then it'll tell you to start verification. So once you do this, it will bring you to this link. Go through this link. It'll give you a free Altium code. Check your email, and then you can install Altium. So that'll be really useful because we're going to try to do like some beginner Altium at the end of this workshop. Another thing, there's also beginner tutorials. So I made something called a beginner electronics guide. I really recommend if you don't know anything about electronics, go through this entire guide. It's pretty comprehensive on what we need to know. And there might be like a little bit more stuff, but we will explain it later on. But this will give you all the basics, like telling you what a capacitor is and what a diode is, or maybe what a transistor is. So it'll give you all the basics that you'll need to know while we are working on our stuff. This will only take like maybe 1 to 2 hours if you skim through it. If you do like the projects aside it to get like an even better understanding, it'll be like maybe 3 to 4 hours. But it's nothing too crazy, and it's all right here, so you just go through it and you can get that done. Um, all right, cool. So yeah, I really recommend like knowing your beginner stuff. So if you have any questions while you're going through this tutorial, please feel free to ask. If you don't want to go through the tutorial alone, I'm even down to, get in a call. We can just go through everything and I can be like your personal tutor. All right. Whatever's works for you is the best, but I really want you to learn. So if, you need to take the opportunity to like try to learn as well, and then we can learn together. So yeah, that would be pretty cool. All right, intro to electric vehicles. All right. So the cool thing about electric vehicles is they're actually universal, and all electric vehicles have the exact same parts. Well, maybe not the same specifications, but like same parts for sure. So let's say we have a bike right here, and we want to electrify it, right? So we're starting off with a base bike. It's just a bike right now. How do we make it electric? So there's actually 4 things that we need to add to make this bike electric, right? The first one is pretty important, and it's the battery. So what the battery does on the bike is provide the entire bike with power, right? So just like how your phone needs power to, turn on and stuff, electric vehicle also needs power. Pretty, pretty good. Two, the next thing is pretty important too, is some type of motor, right? So a motor is what translates that electrical power into kinetic power, right? So for our bike, we could have something like a hub motor that attaches to the rear of our bike, which will provide us that rotational energy, right? But we can't just connect our battery into our motor, right? Because that doesn't really make sense, right? Then that just means like our motor is always powered. It also doesn't make sense because our motor needs specific signals. It can't just take in battery power. So that's where we have this thing right here. It's called a motor controller. So now what the motor controller does, it's a little circuit board, and it's going to take this battery power and it's going to translate it into usable energy for the motor, right? So it's going to tell the motor how to spin. Like if I want to go forward, how do I go forward? If I want the motor to stop, how do I tell it that? That's all the motor controller's job. All right, and now we have one last component that's really, really important. How do we tell the motor controller how to move? We can't just like think, hey, bike, can you move forward? And the bike knows to move forward, right? We need some type of input device, right? So in this case, this could be like a throttle of some sort. So like a twist throttle is a really popular choice. So you can just twist the throttle and it will tell our motor controller, hey, I want to move forward. So with this, that's literally it. Only 4 simple devices, and we can make any electric vehicle with this. Whether it's this bike right here, or imagine we are making an electric skateboard. It's like something like this, right? It's be the same thing because all we're trying to do is move forward and backwards, right? So we have some battery, and maybe we have some motor control, like right here, and that powers a motor, and maybe there's some input device. For a skateboard, usually it's in the form of some type of remote control. And then this twist thumb throttle can make us move backwards or forwards or brake. All right, cool. That's pretty much it. That's the intro to electric vehicles. 4 simple components. Our job is to make all of them or buy the ones that we need and integrate it all together. So integration is a big part of what we do. All right, cool. So let's move on to the first schematic that we are going to make, or the first PCB, or the first circuit that we're going to make. So I made a really, really cool document over here. Let's see if I can find it. That's called Beginner PCB Design Document. And it goes over kind of the basics of what like tools that you should use so you can make a PCB. All right, so you can just like go through this and you can make a PCB. So here we have like circuit simulation software, finding appropriate components. How do I do that? Picking components on Altium. And we also have a bunch of design questions here, and it's pretty much all here, but it's also summarized through this PCB design template. So I really encourage I don't really encourage, I want you to do this. While you're making your PCB, make this template in your own project folder so that while you're doing the anti-spark circuit that I'm about to show you, you can ask yourself these questions. What problems is this circuit solving? What circuit can solve this problem? So on and so forth. All right. And I really want you to go through this so that, you have a comprehensive view on how the circuit works, right? I really believe good engineers are proactive. So we're able to have the device like working because we want it to, not by luck, right? And that requires us to ask hard questions that we might not know the answer to. All right, cool. So that's cool, but I'm just gonna move on. So the first circuit that we're going to make is something called an anti-spark circuit. So you know how I just said, yeah, there's 4 things on our electric vehicles. I kind of lied in that sense because we need to add another circuit called the anti-spark. And sometimes it's part of the motor controller. Or of the motor controller. Alright. But in this case, our motor controller doesn't have it. So let me explain the circuit. So there's kind of a problem when we connect our battery. So let's say, let me see if one node can make a rectangle. Yay. So let's say we have a huge battery right here. And, we have our negative terminal and our positive terminal. And we want to connect our motor controller. So let's say this is our motor controller. Oh wait, I can do this again. Man, this is great. Okay, motor controller. So the thing about our motor controller is that, it uses a lot of power, right? So our standard battery at Electrum is usually 10S or 10 series cells, and that means we pretty much have 42 volts at the maximum. Our batteries can also pull 30 amps at the maximum continuously, or I don't know, upwards to 60 amps, depending on what cells we use, all right? So doing like the worst case scenario, 42 volts at 30 amps. Let me pull out a calculator. We're pulling 1.2 kilowatts, which is quite a bit, right? And the thing is, if we connect our battery instantaneously, so let's say we short circuit these two, we're pretty much going to instantaneously do this 1.2 kilowatts, like all at once, just for a moment, right? Which is a lot of power. for a or for a motor controller to take all at once, right? And it's not really the best situation, all right? Now the reason for this is because the motor controller, it sinks a lot of power. It has something called capacitors on it, which you should know hopefully. But pretty much what capacitors do is they just store a little bit of electrical energy at a time so that instantaneously we can use it later on really fast, right? So these capacitors really help with like making sure the motor controller, when it's outputting really high power to the motor, it has like a constant voltage source it can take from. So that's what these capacitors can be, right? The problem with these capacitors is that imagine our motor controller isn't plugged in for a really long time. The capacitors will be discharged, right? The instant that we plug in our battery, these capacitors act like short circuits, all right? And since they act like short circuits, we might have something like sparking going on right when we plug it in, which isn't the greatest for the motor controller. Since they act like short circuits when they're discharged as well, this this power can all transmit through the motor controller, which isn't really the greatest thing, all right? So that's kind of the problem statement, right? These act like short circuits, and right when we plug it in, something called inrush current goes into our motor controller, and that inrush current can break a lot of components. So obviously we want to minimize that. So this is the circuit that you're designing, right? And it's a really electrical circuit. Or I mean, like it uses a lot of primitive components, and it's called an anti-spark. Now what this does is it does two things. It limits the inrush current by, instead of having this power instantaneously go into the motor controller, it elongates the time that it takes for that power to go in. So if you think about like energy transfer, if we, touch a hot stove for maybe like a millisecond, it won't hurt, right? But if you leave your hand there for like 5 seconds, it's gonna burn. It's kind of the same thing for this, right? Except the opposite. At the very instant that it touches, there could be a spark, which is really, really bad, right? And or it could, because that spark could like break components, and there's a huge voltage there. On the flip side, right, if we elongate the time, that spark won't come because we charge the capacitors over an extended period of time. Hopefully that makes sense. So this is the circuit that we want to make. I really encourage you, when I tell you we're making a circuit, one of the best things you can do is just Google, like, the circuit that we're making. So anti-spark circuit example, or maybe anti-spark schematic GitHub or something like that. And maybe we can find examples of this. So while I was doing that, I found a really good example on GitHub that looks something like this. And we get this schematic right here, which pretty much there's an on and off button, so we can turn on and off the motor controller. And it also limits inrush current. Yeah. So that's also the second thing about the anti-spark. There's an on-off button. I did not mention that, but I mention it right now. So we can turn our electric vehicle on and off. All right, cool. So you're looking at the schematic and you're like, all right, that's pretty sick. Now all I have to do is make it in Altium, right? But you're also you should be asking, what the hell is happening here, right? Like I have no idea because there's just a bunch of components everywhere. I know what you should know is like the basic components. So these are NMOSs or transistors. This is a resistor. This is a capacitor. And this is a Zener diode, right? And this is a push button. But other than that, how do we know it works, right? And that's where, going through the template and answering these questions, it kind of helps you get there, right? And then you make all these things, and then you probably finally get to the simulation part where I ask you to do a small analysis. So let's go through this analysis with you, right? So we have our circuit right here, but I'm going to show you how we can get to the circuit. So we know, right, that we're trying to make a circuit with two functions, an on-off button, and to limit the inrush current for these capacitors. So one of the best ways to limit current is just a normal resistor, right? So what a resistor does, right, is it limits the amount of current depending on the resistance due to V equals IR, right? Ohm's law. V equals IR, right? Another way, and that's the way that this circuit kind of operates, is it uses a natural response of this RC circuit to kind of elongate the time it takes for this circuit to turn on, right? So it uses an RC circuit to do that. And I'll kind of explain to you briefly what an RC circuit is later on. So it's using an RC circuit, and it's using the natural response of it to pretty much elongate the time it takes for this to turn on. Natural response. All right, cool. So let me show you this in action, and it'll make a lot more sense. All right, and then I'll come back to the RC circuit at the very end if it really doesn't make sense. So what we have here are MOSFETs, and all MOSFETs do is when there's 0 volts here. All right, since this is an NMOS, this is going to be off. The moment I flip the switch, you're gonna see something cool. You're gonna see all this current or this voltage rise on this pin, and the MOSFETs will start conducting electricity. All right. So the moment there's voltage on the gate and between the gate and the source, so here there's 2.5 volts and here 0 volts, current can start flowing. All right, super cool. So that's kind of the on-off functionality that we have. So let's implement that really quick in FileStat. So this is just a really good program that we can use to kind of simulate circuits. And I really encourage you to use this while you're simulating your own circuit. So let's build it. So the most, I guess, basic functionality that the circuit has is that on and off button. So I'm going to make that on and off button first. All right. And then I'm going to show you kind of step by step what happens when I change that circuit. So here I'm making a voltage divider. And let's say I make this voltage 42 volts. If I press run on the simulation, you can kind of guess what's the voltage in the middle. It should be 21 volts because this is a 1x1 circuit, right? Here I'm going to put a switch, so the switch can turn on and off. And this needs to be connected here. All right, cool. So now I have kind of a circuit. If this switch is closed, then the voltage here is 0 because it drops because it's shorted to ground. If this is open, this becomes 21. All right. So now I have an on and off switch that's pretty effective at, turning stuff on and off. Now the reason why I have this voltage divider as well is because you can think to yourself, this voltage is pretty high. It's 42 volts. All right. So by limiting that voltage to 21 volts, we have something that's like a lot more manageable for the transistors. If you look at transistors normal like V threshold, or the voltage that needs between the gate and the source to turn on, it's pretty low. So you don't want anything too high voltage. You could probably configure these resistors even further to have a better result. We're just going to go with this for now. All right, cool. So now we have our voltage divider. Now we want to turn it on. We want to use them to turn on NMOSes. Let me see if I can hotkey it. I guess not. So here we have NMOS. Let's just use one for now. And this NMOS, all it does is it turns on and on, right? On and off. So here it's connected to gate. And in this example, I'm using a capacitor and a resistor to represent our load, right? Our motor controller will take some current. That's what the resistor is doing. It's taking current. And our capacitor will represent the capacitors on our actual motor controller that help kind of stabilize instantaneous changes of current and of our load. So I'm going to connect this up. Boom. Once this is powered, we are going to go through our MOSFET, right? And that's pretty much it. Darn it. All right, so now let's see what we have. So now we have our load that's powered, right? This capacitor switch or has power, so let me stop that. So if we look at our capacitor right now, there's really no charge. Look at the bottom right. There's like no voltage across it. There's no charge. Current can't flow because this NMOS is closed, right? But now the moment I flip the switch, boom, a lot of current can flow, right? And if you notice at the very beginning, there's a huge inrush of current, right? Let me, excuse me. Let me reset the circuit and play that again. So when the switch is closed, this is tied to ground, right? You can see this ground path. But the moment I open the switch, huge inrush of current as the capacitor charges, all right? And then after the capacitor is fully charged, there's not as much inrush. All right, so let me explain this effect now. And this will help explain the RC natural response. So capacitors, I know in the tutorial, all I really said is that they store electric charge for a really short amount of time, right? But what I didn't tell you is that it takes some time for that electric charge to actually charge, right? It's not instantaneous, right? So what I mean by that, let's look at this graph where voltage is on this side and time is on X, voltage on Y. So if it was instantaneous, let's say I apply a charge on a capacitor, it'd go from nothing to instantaneously going to the maximum voltage the source is applying, and then it continues. Real life's not like that, unfortunately, and you'll know if you take like a first year circuit course, they'll teach you this. But capacitors actually take some time to ramp up. All right. Now it's this time right here. And it's this time right here where there's a huge inrush current, right? This is like its maximum increasing time. Like around this like beginning time, right? So that's why we see a huge inrush current. And as we charge our capacitor more and more, we see less of that inrush current. What's really neat is at the top of this is around 5 tau, right? 5 tau. All right, and what's 5 tau? 5 tau is kind of what our RC circuit is making. So tau is just equal to RC, and its unit is time. So if we have a capacitor that's 1 farad, and we have a resistor that's 1 ohm, right? Our tau will be 1 second, right? So it'll take 1 second for us to get, like, at this point right here. In 5 seconds, we'll reach our top point right there. All right, cool. This is also a function that can be described with math. So I think the equation is Vt is equal to Vc, so the voltage of the capacitor, and it goes up by e to the power of t, so like the actual time that elapsed over tau, or r over RC. T over tau. Make sure I'm not giving you false information. Okay, V naught E negative T over tau. Cool. Negative T over tau. And tau is just a constant. So as time elapses, you can see this is just an exponential function, right? So our VC is just going to continuously increase. And I should say here, this isn't VT. Oh yeah, that's VT. This should be our V source, I believe. So our V source times this exponential function is equal to our VT. I guess the better name is VC for our voltage capacitance. All right. So yeah, our capacitor doesn't charge linearly. It charges exponentially. At the very beginning, there's a huge inrush of current. VC, or the voltage of the capacitors, equal to the voltage of the source times E minus T over tau. So however much elapsed time. Tau is described by our RC circuit, right? So our capacitor and resistor in series, that's what tau is going to describe. So what the resistor does is limit the current, right? It resists the current, and it can limit it. What the capacitor does is it charges over time. All right, cool. And we see that with the simulation. So now that we understand kind of the math between it, not really the math, but the graph behind it. Let's say I press run. You can see this huge inrush of current. And let's see if I could even put a scope right here. So, yep. Let's run it. So what you're going to see is a huge inrush, and you're going to see this exponential curve of the voltage right here. Right here, it's showing me negative voltage. I don't know why, but you can just imagine it's supposed to go up. All right. Yeah. Let's see if I can get it. Yeah. Anyways, don't matter too much. You can just imagine it goes up. Remove scope. All right, cool. So there's a problem, right? This huge inrush of current. We don't want that. And if we look at the time of the simulation, it takes about this much time, like 16 milliseconds to fully charge, all right? Or reach steady state. That's what we call steady state, right? Which isn't the greatest because that's a pretty short amount of time where it's fully charging. And if you look here, there's a huge inrush of current. We want to minimize the inrushes of current as much as possible, all right? So that's where this circuit comes in. And there's two important parts to it, right? And it's to regulate how fast this NMOS turns on and off, right? So you know how I said transistors, all they do is turn on and off? I also kind of lied to you there, all right? Because transistors don't just turn on and off. There's actually a region of operation for transistors, all right? So there's a cutoff region, and there's also a region right here that's called the ohmic region, or the triode region. Let me see if I can get a good image. Saturation breakdown. NMOS regions of operation. Yeah, there we go. This is a good image. So right here we have something called the triode region, right? And at this point, right, the VDS isn't great enough for the transistor to like start conducting a lot of current, right? And this is also determined by VGS, right? So if we look at VGS right here, we have our gate right here, and we have our source right here. So the voltage between these two pins is what is going to determine that VGS, and it has to go over this threshold or VT, and reach that. So what we're doing, if we like kind of staggerate like how long the NMOS has to turn on, we're kind of limiting the current that passes through this NMOS in the first place. All right. So let me say that again. If we slowly ramp up the gate, it's not going to instantly turn on, right? It's going to slowly ramp up based off this exponential, or I guess this is a ln function more like, so based off this natural function. All right. So how do we do that, right? So one of the ways is what I told you right here. We can add an RC circuit, and that's how that circuit before kind of works too. So what they did is they added a capacitor right here, which is 1 microfarad, and they added a resistor right here, which is 1K, right? So if we calculate our tau, it's equal to our R times C. So it's equal to 1 micro times 1K, which is equal around 1 millisecond, right? So this is going to make the gate kind of like take up to 5 milliseconds for this RC circuit to turn on. But that's also kind of a lie, because it's going to take much longer in real life, in actuality. Yeah, and you'll see why. So I'm just going to attach this RC part of the circuit so that you can kind of visualize how this looks first. And then we can add in more later on, or the diode. So if you notice, once we add this RC circuit, this clamps it to off, right? What happens? Our capacitor right here is going to fully charge, all right? So for as long as the switch is closed, this capacitor is going to fully charge. And that's because the path of right here. The battery goes to here, it goes through these components, and it charges this capacitor right here through this ground. So there's a path of electricity to flow. When the capacitor is fully charged, it becomes an open circuit, so no more no more current can flow. And since this capacitance is so much less than the motor controller capacitance, this capacitor is pretty much guaranteed to fully charge first and turn into an open circuit, breaking the circuit. All right. Now, obviously, we don't want our current to flow through this path. We want it to flow through this MOSFET. So let me slow down the simulation speed, and look what happens when we turn on the switch. All right. Let me give it some more speed. This gate right here is going to slowly charge or slowly ramp up. And this capacitor, instead of charging up, it's actually discharging right now. Which is really cool, right? So the more that it discharges, right, the potential right here is slowly lowering. The potential right here is slowly highering. Since the voltage across the capacitor is these two values, like this value minus this value, this voltage will start decreasing, right? And it kind of like follows the path of that RC circuit that I was talking about before. So slowly ramps up this NMOS, and you can see that it's slowly in saturation, but the IDS value is slowly ramping up as the VGS starts increasing, right? Because although it crossed the threshold right here, it needs to slowly ramp up, right? Using this curve, or the ID, this is the same as the IDS. Right, so the more VGS we have, the more current we are going to be able to flow through. So with this method, look, it's already 500 milliseconds, but our capacitor is not fully charged. It's just slowly ramping up and chilling. I might have also not reset the simulation, so it might not be fair. But anyways, it'll take longer for the capacitor to charge. So in this case, Right now it's going to take a while, still ramping up. See if we can, and we can see the curve being super slow. That's visualized in this scope right here, or in this graph, right? So after, kind of wait, after around 2 seconds, our circuit is like pretty much charged. So the cool thing about this, right, is now we have a full circuit that kind of takes a long time to charge, right? And we minimize inrush current. We don't really need to turn on our device like instantly. If we just like wait a second so that there's no spark, it's not that big of a deal. Now, obviously, we can optimize this, right? So maybe the most ideal thing isn't having this to be taking 2 seconds to charge, right? Maybe you want it to charge in like 500 milliseconds. That's probably fine too. You just have to do more analysis to see what's right for you, right? So that's really cool, but there's one final problem with this circuit. As this capacitor fully charges, right, and it becomes 42 volts, the voltage here is pretty much 0 in reference to ground, right? Because it's just passing through this NMOS. But look here, right? Our VGS is really, really high. It's around 17. It's going to reach 21 volts because of this voltage divider, right? And once this capacitor has fully discharged, or it'll be 21 volts right here because of this voltage divider. This VGS, or this gate voltage, will always be 21 volts. Now that's kind of a problem, because if we look at, I guess like, I'm just going to steal the transistor that they use. If we look at this transistor that they use right here, and we scroll down to the VGS maximum rating, the maximum rating is plus minus 20 volts, right? So we kind of broke that rating by 1 volt, which isn't the greatest. If we also look down at the other charts that we have for VGS, right? We notice we don't need that high of a VGS to have our drain current to be super high, right? Because this is exponential, right? So even at a gate to source voltage at like 6 volts, we're going to have a ID of upwards of 1,000 amps if we really, really need it instantaneously, right? Obviously, this is with a VDS of 25 volts. We're doing 42 volts, but the principle is still kind of the same. So in reality, right, our MOSFET is rated for 240 amps, or it could be rated to 330 amps, depending on like if we add a heatsink or whatever. And we can reach that pretty easily by having it clamped to 5.5 volts instead of reaching 21 volts. All right. So right now we have this at 21 volts. All right. So that's where this really cool component comes in, and it's called a Zener diode. So what a Zener diode is, so I think I explained diodes before in my beginner tutorial, but they have a forward voltage drop, right? So you need like a certain voltage to reach that diode like breakdown zone. So a very normal voltage drop for diodes is like 0.7 volts. So what this would look like is voltage drop or voltage through. And this could be a voltage diode. So what this can look like is until the voltage diode reaches 0.7, right? That's when you have a rise of voltage, right? So the voltage can go through the diode, and it'll take 0.7 volts to do that. Okay. So this is like kind of a normal diode, right? And then once it reaches this, it lets all the voltage through pretty much through the diode, since it reached its breakdown zone, 0.7. Now, what the Zener diode does is it's really interesting. It has a backwards breakdown zone. And this is called a reverse breakdown. Now, this is really useful because at this reverse breakdown, it's going to clamp the voltage at this certain level. It's going to clamp the voltage through at a certain level, right? And it's pretty much going to use very little current, but still clamp this voltage to this certain level, right? So this way, if we want to make our like Zener diode like threshold voltage or our V through voltage to be like 5.5 volts, we're going to reach the specifications of our transistor right here. You know, around 5.5, 6 volts is fine. And we're not going to over the kind of the maximum voltage rating for our VGS or our V gate source. So that's kind of what the Zener diode is. Now, the reason why, you know, we don't just like spec our voltage divider for this is because the voltage divider is going to kind of provide us a constant source of 21 volts, right? If we said, hey, we want this to be 5 volts, right? What happens if we like throttle our vehicle really, really fast? So once we do that, like if we throttle our vehicle really, really fast, a really fast voltage drop will happen over our battery, right? Because since it's applying so much current, it's going to naturally drop in voltage, all right? That means this voltage divider will also drop in voltage, right? So let's say we have a nice steady 5 volts, and then suddenly we throttle really fast, then it drops to 3 volts. Since this voltage divider is specifically tied to this voltage source, if this voltage source drops in voltage, the voltage divider will also drop in voltage, which isn't the greatest thing in the world. Because you imagine all our currents going through this NMOS transistor, right? And if our VGS, our V threshold, isn't reached of like, in this one it's 1.5, but I think for an actual one, VGS, gate threshold voltage is like 2.1 or something. So imagine we don't reach that threshold voltage. Our electric vehicle is just going to stop for no reason, right? And you can imagine this is super dangerous, right? Because we start accelerating, and you know acceleration can be constant if you know cap m, and then we can have kind of like a velocity that's suddenly increasing, right? But imagine our acceleration just like suddenly stop, right? Yeah, let me make a better graph. So this could be like our acceleration, and our acceleration suddenly stops, it drops to 0. Our velocity is also going to suddenly drop to 0, which isn't the greatest, because now we're going to feel that like if we're on an electric skateboard or electric scooter, and that's going to feel like a force that's pushing us backwards pretty much. So that's not really ideal, and we obviously don't want our electric vehicle to just like die in the middle of us using it, right? So what is really smart about this circuit, right, is that we have a voltage divider that's providing 21 volts. In our worst case scenario, our battery is going to drop to like 30 volts, because that's just how batteries work. The more we use it, the more voltage drops from it, and that's how we like know the charge of the battery. So even at 30 volts, this will still have a good 15 volts at our voltage divider that we can use, right? So our gate's pretty much guaranteed to always turn on. Now again, the problem is we might reach the maximum spec of the gate. So that's where the Zener diode comes in. And we can spec our Zener diode to have a V threshold of 5 volts, so that this pin right here is always going to be kind of clamped down to that 5 volts, right? Ooh, Zener diode right here. So if we add the Zener diode right now and reset and turn off our circuit, nothing really special happens. It's the Zener diode, it's just chilling there. But the moment we turn this on, it's going to quickly charge up. But notice what happens at our V gate, right? Instead of going to that insane voltage of like 21 volts, our Zener diode is going to eventually break down, right? And it's going to allow some trickle current to go through it down to ground. And it's pretty much going to clamp this gate pin at that 5 volts. So right here we see that there's microcurrents going through this Zener diode, but that's fine, because the current through here is pretty low, because this voltage divider is like 1 million to 1 million, so there's not that much current going through due to Ohm's law. And this V gate is now clamped at 5.5 volts, which is perfect for our application. All right, so that's kind of the entire anti-spark circuit. So that's pretty cool. So we have our switch, our default state can be closed, right? So when it's closed, our circuit doesn't move, no current flows, our devices don't turn on. The moment we flip the switch, this MOSFET slowly ramps up, slowly turns on. And you can see that at VGS, it's slowly turning on. And with that slow turn on rate, it slowly conducts current over time, right? So you can see VDS slowly ramping up at the moment VGS reaches threshold. Now this function is exponential for the transistor, so it's going to exponentially allow current to flow, but it gives the time for this capacitor to actually charge. All right. So after, I don't know, a long time, our device, a long time for the simulation, but like for us, it's pretty short, our device will be fully charged. All right, cool. So that's kind of the anti-spark circuit that I fully went through. That's really nice. Hopefully that makes sense. If not, again, feel free to ask any questions. Since this is a recording, I can't really answer questions, but you feel free to DM me Discord anytime. I'm really active, and Demir should be right beside you when you do the actual workshop in person, if you are in person. Okay, what else am I covering? Let's see. All right, cool. Cool. So yeah, that's the anti-spark. That's kind of how you read schematics too. So you want to break down the schematic in simpler parts. So that's kind of what I did with you right there. I looked at, hey, this is a voltage divider. I can make this part of the schematic first. What does that do? We add in more transistors. Suddenly, if we want to like slow down the ramp time, we can have a RC circuit. And if we want to clamp the MOSFET gates, we can with the Zener diode. Now we fully understand the circuit, and I didn't even do any math, right? That's just from the simulation. Should you do the math? Probably. That would be a good idea. But if you don't, I don't blame you because the simulation pretty much shows you how to do it. I would say get the threshold voltages, know what components go where, and then you can use the simulation and double check your work. Cool. One last thing I didn't mention. Why did I only put one MOSFET here? It's kind of just for like, because I was just showing you. But you can imagine the more MOSFETs I put in parallel, right? The less the resistance over the MOSFETs are. Because, you know, components in parallel, the resistance is equal to like 1 over R1 plus 1 over R2. And each one of these transistors do have a resistance on them, although very small. It's RDS, right? So it's 1.15 milliohms. So it's a really low resistance. But because it has that resistance, it'll sink some power. Okay, cool. I think that's it for the circuit. So we're going to move on. Ultium. Ultium. So I think the first thing that I want to make sure that happens is that you are invited to our workspace. So we have a really nice workspace here with a bunch of projects, right? Once you're invited to your workspace, please make a new project and title it your kind of like project names. Like if you're on Stealth Bike, or Bakfiets, and then kind of the numbers behind that. So like you can say Bakfiets Winter 24. I think that would work, or 2024 or something. So here I can invite you here. So this is kind of, Altium has a really nice thing called Altium 365, and it has this web viewer where you can kind of view like everyone who exists. I'm kind of doxing everyone's email right now by accident. Whoops, I'm sure it's fine. They will forgive me. But I will invite you to the workspace. You'll get an invite in your email. Make a project, then download and install Altium. So once you install Altium, did Altium open yet? Hello? Once you install Altium, you can open it like I am doing right now. Your computer, you know, if it's not the greatest, or if it's a Mac, no offense Mac, but they can't open Altium, then you would need to get like a virtual desktop to open it, or just wait a while, to be honest. You can also virtual desktop onto the school computers, but I'm not sure if they have Altium. So let me just show you around so you kind of get the feel of what the space looks like. So at the top right, we have kind of our cloud, right? So what we can like actually look at. So here I have electromobility. I also have Midnight Suns Altium because they're kind enough to share it with us, and they're super cool and they're really good at circuits. So I really encourage asking them questions as well. So yeah, we have our workspace and this workspace. When you first launch Altium, you probably won't see this workspace, and it's going to ask you to join one. But that shouldn't be a problem because you should be able to do that. Right here at the top left, you have a bunch of buttons so that you can open projects and stuff like that. And you also have your project viewer right here. So if you see the workspace electromobility, you can create or open a project. So here, if I press open project, I can open one of the projects that we made in the past. So I encourage you to just open it and play around with it. Altium has Git built into it, so any change that I can make, I can save it to the server so that everyone else can see the change. So it really makes kind of looking at other people's work very, very easy. Why is it freezing? I'm trying to open the schematic. Oh, why do I have two of these open? Doing nothing. Okay, cool. So this SIG doc is the schematic doc, and this is one of the schematics that Demir made. It's pretty much the anti-spark circuit, pretty much the exact same actually, that we have in the simulation, because it works, you know, we're just going to make it very fast. To navigate, you can hold right click and it moves your interface, which is pretty sick, because, you know, I like moving. You can hold control and zoom in. And you can also click on the components and move them around by, holding drag and moving it. I encourage you to just play around with it. You won't break anything as long as you don't press save to server, so that should be fine. Here you can look at like PCBs that we've made. So this is the one that I made for the anti-spark PCB, and you're going to make the exact same PCB as well. All right. So this is kind of an example of what one PCB could look like. So your goal this term, or I guess in the next 4 weeks, is to make this PCB, right? And the entire point is like, obviously I have it made right here, but I want you to make it because there's no point in me just being like, oh, I got the PCB then. That's it. That's the entire term. I want you to make it by the end of the month, or maybe not the month, or the start of the next month. We're going to have this PCB. We're going to manufacture it yourself. You're going to solder your own PCB, right? And you can customize it however you want, whatever vision that you have for the PCB. I want you to make it, right? And you're going to make it from scratch, which is going to be super cool. Anyways, yeah, I don't know why I got so excited. So this is like a PCB that I made. You're going to make the exact same PCB, but try and make it better. I think you can. I'm not the best PCB designer ever. Yeah, so that's pretty cool. So what else do I have to cover? That's pretty much it for this workshop, I think. I just wanted to show you like basics around Altium. You should be able to move, get the invite. Next workshop, we are going to go over making schematics in Altium, right? It's pretty like not that bad, but you need to know things like making components, for example, and how to place them and making net classes and kind of get all the terminology out there. So that will be next workshop. Other than that, thank you very much for listening. Hopefully the circuit made sense. I think that's it for this workshop. Yeah, that's pretty much all I have. If you have time with the mirror, you can build the anti-spark circuit on a breadboard and analyze it with an oscilloscope. That'd be super cool. But yeah, we should be ready for workshop 2. So let's look at briefly what workshop 2 is going to be. It's going to be overview of the circuit design process. So kind of what the document I showed you before. I'm going to go through it more. Getting used to using Altium. I'm going to show you some cool stuff. And we're going to select some components. We're going to route the schematic. We're going to finish the schematic by next workshop. So by next workshop, we're going to have this entire schematic done. All right, cool. And then we're going to have our PCB done. I'm super excited. So just a quick exercise if you have extra time. Go on Falstad, right? Make the circuit yourself. Get the simulation to work, right? This is pretty much the schematic that we're going to make. And then we're going to transfer the skills that we use on Falstad to Altium to make that schematic. All right, so that's kind of your low homework at the very end. Other than that, thanks for coming. Ask me any questions you do. And see you next time, which is next week.